Hello everyone, welcome back. In today's series, we'll be talking about the transformer architecture, which is the basic building block for large language models, also known as LLM. And large language models, as you must be knowing, are used in all generative AI tasks that we use today. So you must be hearing of these tools and software such as ChatGPT, Bard, and various other generative AI models that work wonders and magic for us and do a lot of complex intelligent tasks such as text summarization, text generation, question and answers, providing insights to certain data, and also certain other things like code generation. So how do these large language models work their magic? For that, we need to understand the transformer architecture, which was conceptualized from the paper Attention is All You Need. So I've simplified the transformer architecture into a simple block diagram, and I'm going to be explaining what is the transformer architecture and how does it actually work and how does it enable the LLMs to work its magic. But before we proceed right ahead, not forget to subscribe to my channel for the latest of data analysis in Excel, Power Query, Power BI, and Python. Let's delve right into it. So the transform architecture at a very simple conceptual level has the embeddings layer, an encoder, a decoder, and a softmax layer. Also to note, the transform architecture comes in various variations. It can have only the encoder only transformer architecture, the encoder and decoder transformer architecture as we see here, or the decoder only transformer architecture. If you want to understand the differences between the three versions, do let me know and I'll make a video on that as well. I've also made a lot of videos on ChatGPT. You can take a look at that as well. I'll leave a link in the description. So first we need to train the transformer with a corpus of text. So let's take a look at the simple text. Say we pass this text to the transformers. So what exactly happens? The cat chased away the rat. First we need to break down these words in the sentence and tokenize them. So what is the meaning of tokenize? So tokenize is the actual words are converted into numbers, because the transformer architecture, which are neural nets, cannot work with actual characters or letters or words. They need to work with numbers. So the tokenizer converts each word into a number, and the number represents the position of each word in the dictionary of all the words of the corpus. And now in the next step, what do is each token that is being created is passed to the embeddings layer. The embeddings layer is a highly trainable high dimension vector space. So what does this mean? Is now the tokens are now mapped to the vectors. A vector is a mathematical representation of tokens. The general vector length is 512. So let's because these vectors are now used for further computation. So once the embedding layers map the generate the vectors, and this concept was already there earlier for any text use cases for machine learning. For example, like word to vec, you might have heard of those kind of algorithms. So now the vectors that are generated via the embeddings layer, with that we add the positional encoding. So the positional encoding is nothing but the unique position of each word in a high dimension space. So the positional encoding is added to the vectors, which are mapped to each of the token, and this information is now fed into the encoder layer of the transformer. So here we use something called as self-attention. So what is self-attention? So to understand self-attention, basically now the vector representation of the tokens are passed into the self-attention layer of the encoder, which actually finds out the relationships between each word. So you can see in a two-dimensional space, here the vector is a multi-dimensional space, which is very hard to visualize, but let us consider only a two-dimensional space for simplicity. So in two-dimensional space, if we represented two words in this manner, it's possible to calculate the distance or the angle between the two words and find out which of the words are closely associated with each other. So that is basically what the self-attention layer does. So let's take a look at how it does that. It does the same for every single word in the corpus. So it finds out the relationship of every word with every other single word. So it finds the relationship of the cat chased away the rat. Then similarly it does that for the next word, cat. What is the relationship between cat, the cat chased away the rat, and it goes on and on and on until it assigns something called as attention weights to these to each word, and this is called the attention map. So this is done by the self-attention layer, which helps it encode language, because earlier in something like its predecessor called the recurrent neural network, each word was looked at only with its previous word. But here, using the self-attention layers, the relationship of each word to every other word is calculated by the self-attention layers. And this is not only done once, but it's done for something we call as multi-headed self-attention. So multiple times it is done, and the reason for this is that it learns different aspects of language. During one pass, it may learn something such as grammatical syntax of the language. During another pass, it may learn something like as the significance of each word, or some rhymings, or some tense. So it learns different characteristics of language, and that is encoded in the encoder layer. Then the information from the encoder layer is passed into something called as a feed-forward neural network, and this is a neural network which then generates a vector of logits. So it generates a probability matrix which contains the probability score of every word or every token, and that is then passed to the decoder and the softmax layer. Now the softmax layer scales the probability so that we get an output in which each token is represented by a normalized probability score, and the token which has the highest probability score becomes the next predicted word in the sequence. Okay, so the cat chased away and it will predict rat, or the next word after that. And then the output is then passed back to the input layer of the decoder, and this keeps on happening time and time again until the loop completes and the end of sequence token has been generated. So this is the basic and the most simplistic explanation of the transformer architecture and how it works. And there are multiple use cases. As we mentioned, we can have only the encoder only transformer architecture, which is used typically for sequence to sequence kind of use cases, such as and you can use it for text classification, extraction of text from a corpus of data, but you need to add a few more layers above that. Then we have encoder and decoder architecture you have seen here, and this can be used for text summarization or text translation. And finally, we have a decoder only transformer layer, as we have seen in the GPT series, which is used for a lot of things such as text generation, question answering, etc. If you want me to make a video on that, do let me know, and also the different use cases for each of the transformer architecture. I hope you enjoyed this video. If you like the video, do not forget to subscribe to my channel for the latest of data analysis in Power Query, Excel, Python, and Pandas. Thank you.